Oi. Well, that was it. Good morning. Kalle Hashmi is my name, and I'm working at IRENA, and as you know, everybody at IRENA is working with renewable energy. And I'm going to lead you through this morning how the world of energy looks like, the main actors, and what are the future trends that we expect, and hopefully they will lead to a new industrial revolution. That is the idea of this presentation. So it's going to be very broad-based, and I'm not going to make it too technical because that has a tendency to make people sleepy. So I'll keep myself to some generalities to make it easier for everybody to follow. Okay. Anything and everything that you see around yourself that has been created by a human being is energy packed in a different form, but it is all energy. Anything and everything created by human beings is repacking energy. So please have it in mind that nothing that you come across, whatever it is energy in one form or the other. And as you know, the laws of thermodynamics, we can only transform energy. We can neither create it nor destroy it. If you look at the first industrial revolution that started around 1850, and for some reason it started in England. And the question is, why did it start in England and not in Germany or in France? It started in England for one simple reason, that they had succeeded in beheading their king, Charles. And thereby the power had moved from the monarchy to the parliament. The parliament was making decisions, and the parliament was much more liberal in thinking and in letting people run businesses and in creating businesses than the monarchy was. Monarchy had an enormous interest in manifesting its power, and the monarchy decided with whom to share power and with whom not to share power. And one of the biggest things was that the monarchy decided who gets to be rich and who doesn't get to be rich. And agriculture was the mainstay for the monarchy to make people rich by giving them tracts of land to grow on. Or to give them the right to sell salt in the country, for example. So in that sense, in Germany and in France, monarchy was extremely strong, extremely powerful, and extremely obstructional when it came to open thinking and developing things. So that was one of the fundamental reasons why it started, because Britain had come a long way. If you look at Isaac Newton and lots of other people were active already, creating lots of theoretical knowledge in England. And there were many, many societies where industrial potential and other industrialists could meet people from academia, researchers and others. So the society had an enormous amount of openness. The other advantage was that they had coal available in the coastal region, which made it easier to ship it. Because you didn't have, railway hadn't come as yet. There were no trucks available. So you have to remember, it was horse-drawn system. So you really could not carry the stuff very long distances at the back of a horse carriage. So, but in the case of Britain, the coal was available in the coastal regions, which made it easier to put it in ships and take it to the bigger cities, because they were also located where there were waterways. So the combination of the two, cheap energy in the form of coal. Before that, wood was the mainstay, and wood was very, very difficult to move around. So it was easier to move it. Anyway, if we look at it, if you look at these two graphs, you will see that the increase in per capita GDP on the right hand side, if you were to look, that is somewhere the Industrial Revolution starts and then it spikes up straight away. And then you see the energy consumption at that time, it also spikes up. So there is a very clear relationship between energy intensity and growth of GDP, which means, in simple economic terms, that it is not possible to have economic development without some sort of increase in the use of energy. It's very simple, because that is what you actually do. You keep on transforming more and more energy into goods which people can consume. And that is why these two are linked exceedingly well. The growth between 1000 to 1500 also increased for the simple reasons that you started creating cities, people moved to urban areas, more and more agricultural land was brought in, and there were triple harvesting which had come in, that you could plant and harvest crops 3 times a year, which wasn't done before. And there were some other simple technical developments, like they had learned to put nails in the horseshoes, which they didn't know before that. So that improved the performance of the horses. They had developed harnesses for the horses, which they didn't know before. So in that sense, windmills had come, which started providing power, and so on and so forth. And then they developed the textile industries. They discovered organic colors that they were using, and that led one thing to the other. And then the universities came, so the educational system was established. So urbanization actually started, and with that the economic development. But it spiked with the Industrial Revolution very, very quickly. And one of the biggest things actually, since you are technical people, which made it possible was the Haber-Bosch process. That was how to fix nitrogen, and thereby to create artificial fertilizer. If you're talking of disruptive technologies, the biggest disruptive technologies during the Industrial Revolution was the Haber-Bosch process, which made it possible to produce artificial fertilizer, which was not possible before. And that really led to the possibility to be able to feed people. Because if you urbanize, then you have to feed people. And that is what happened. Okay, where are we going now? Now we have left the Industrial Revolution and we have come to today. And let's look at the situation, what is happening. The first thing is that the demand for energy will continue to grow. Why will it continue to grow? Because the population is continuing to grow. And we expect that we will go from 6.5 billion people to 9 billion people by 2050. You're going to add 2.5 billion more people. And with that, there'll be industrialization to support all these people. They will need housing, they will need clothing, and they will need food, if nothing else. And then it is the quantity of fresh water is what it is. And now you add 2.5 billion people to the same amount of fresh water that you have today. That would require some sort of desalination, because you do not have enough fresh water to feed all these people. So in that sense, that would require energy. The other is that we expect the transportation to increase as the number of people increases, and the number of cars, if nothing else, may approach 2 billion units by the year 2050. All this will require energy, which means that the demand for energy may double between now and 2050. Which in turn may lead to price volatility. It may not be very easy to support all these people with energy all the time. In turn leading to environmental stresses to a very large extent. And that would lead to a pressure to do something about the environmental issues much more. Otherwise the temperatures will rise up. It really doesn't matter when they say the world temperature has risen by 0.8 degrees. You don't think so? It's too much. I mean, as an individual you go around, what is 0.8 degrees? And 1 degree here and there, what is the difference? The trouble is that it is the average of whole of the world. It is not the same temperature increase everywhere. Some places are getting much higher temperatures, and some places are getting smaller increases. So it is 0.8 is the average of the world. So some places are in absolutely disastrous situation when it comes to temperature increase. The challenges that we are facing is, how do we get to lower energy intensity? That is one of the major things. When it comes to lower energy intensity, then we are moving towards energy use to a very large extent. How can we get appliances and machinery that we're using in industry to deliver what it is delivering today with less energy input? That is what we are looking for, to make things much more efficient, from vehicles to everything else in the use of their energy. The other is, we do not want to have too much carbon emissions. How do we move energy system from high carbon to low carbon emissions? And the third is, at the same time, how do we provide a decent standard of living for 9 billion people? That, ladies and gentlemen, is the equation that you will be fulfilling long after I'm gone. Congratulations. So it's not me who is going to do it, it's you who is going to do it. So it's nice for you to know what is awaiting you when you leave this university, if that helps. This I have spoken about. This is how the world is going to look like if you don't do anything. And it is 9 billion people. If nothing else, you will have to feed them. I mean, forget about everything else. Fancy stuff like cars or riding airplanes or having private jets. Just feeding them. Is that 2 billion people, if we increase it, they will require 1 billion tons of cereal every year. And they will require 200 million tons of livestock for milk and other products. And now if we were to look at this thing, this is the amount of water that you have. 200 cubic kilometer of water that you have. You had the same in 2007 and you have the same in 2050. And this is what has happened to your population. And this is the amount of water which is fresh water, but this is the amount of water which is available in the seas. And unless you put back the salt into the sea, I think there is enough water. So it will have to be desalinated. There is no way you have water to go around. Sure. Could we take them afterwards so that I run through, because there are tons of slides. Can you, or you must have it now? Okay, the next question is, do we have enough energy for 9 billion people? You have been hearing for the last 5 years that we are running out of energy and we have reached a peak production levels for oil and there is not enough oil and so on and so forth. And the world is running out of, and it is a finite source and so on and so forth. All that has been going on for the last 5 years. But if you were to look at the reserves of oil, they are actually increasing and not decreasing. We are using about 75 million barrels a day, and the reserves today are 1.64 trillion barrels, which is available. So even if you increase the population to 9 billion, I'm not counting the gas on the other side, there is enough oil to support all of us for the next 100 years. So it's not running out in the next 10 years or 15 years or so on and so forth. And it is increasing each year, surprisingly. They're finding little more. They've become a lot better at finding. And the gas is also increasing. So in that sense, there is no shortage of oil as far as that is concerned. 1.64 trillion barrel is lots of oil even for 9 billion people. Okay, so we have enough energy. Wonderful. So what's the problem? The problem is CO2 emissions. Since Industrial Revolution 1850 to 2013, if we were to take the fossil fuels, we have produced 1,100 billion tons of carbon dioxide. That is what we have produced in 163 years. Now we have a much higher level of energy consumption than what we had in 1850. You have to remember that. It's not the same low level, it is much higher. Now if we are starting at the same high level for an additional 2.5 billion people, then we will be producing 3,000 billion tons more to support these people. And how long will it take us at the current consumption level for these additional people? 75 years to produce additional 3,000 billion tons of carbon dioxide emission. We took to produce 1,100 billion tons 163 years. Now we will be producing 3,000 billion tons plus in 75 years. Huh? Now at the same time the question is, what is all this oil worth which is lying in the ground? It is worth $164 trillion. Now the question is, it's carbon basically. Is carbon worth $164 trillion lying in the ground? Do you let it lie in the ground? That is one option. Okay, forget about $164 trillion. Thank you very much. I can live without it. That's one option. But if you exercise that option, then you end up with 3,000 billion tons more carbon dioxide. Are you with me? Are you seeing the equation that we are facing? Because most of the time you hear a micro argument, but you have to look at the stakes. What is really at stake? And the stakes are very high. $164 trillion is tons of money. Sheikh Yamani, who was the oil minister in Saudi Arabia, once said, "We left the Stone Age not because we ran out of stones, because we had found better things to do." We have reached a point where the question is, are we going to walk out of oil age not because we have run out of oil? I don't have an answer to that question, let me have it said. But let me get you through how the real world looks like. This is how the real world looks like. And nobody is going to let this $164 trillion just go to the drain. It doesn't look very plausible to me, but you never know. And at the same time, you have carbon emission. So, what is happening? The first thing that is being looked at very seriously is carbon capture and storage. And where are you going to store it? You are going to store it in the same holes where you are extracting oil. If you are not extracting any oil, you can compress carbon dioxide and pump it back into the same holes. And who will do it? The oil companies, of course, would do it. But they would not do it if you are not going to pay them for it. You pay them for pumping oil and you'll pay them for carbon, which means you will require a pricing on carbon. It will become a valuable commodity. Somebody would have to pay for it to be captured, transported, and pumped back into the holes so that it disappears. The question is, can we take 100% of carbon? No, we cannot capture 100% of carbon. How do you capture carbon from one single car which is driving between here and Sharjah? Unless you use half the car to capture whatever is coming out of the car. So anyway, there are portions where you won't be able to recover it. But this is what it is. Okay, the summary so far is, are we running out of energy? The answer is no. Can we support people with energy? Yes. Is there a cost for it? Yes. Carbon dioxide emissions. And what are we doing about it? We are looking at carbon capture. And will it take place? Yes, if somebody pays for it. Very simple. Are you with me? Or is it still technically too complicated? Okay. Now let's look at the industry. You people are here to change the paradigm of energy industry. That is what they teach you, that is what they train you, and that is what you believe. That you will walk out of this place and you will discover something. So there will be angels would sing a song and heavens would open up and the whole world would look very different in just about 10 days' time. But before you get to that, it would be interesting the kind of people that you will be meeting along the way, that you will be dealing with to bring about this change. So let's look at the energy industry. How does it look? Or the energy system? I have used the word syllogism, which is a Greek word, which in simple English means conclusions. But since I'm also from the academic world, if you can use a more difficult word, why not? That is what they teach you in educational institutions. Keep everything more complicated because then you seem literate and educated. That is the trick of separating yourself. Though Einstein said keep everything simple and not simpler. But there aren't that many Einsteins. Most of us are like us. So, and our role is to make things more complicated than what they are. Anyway, what is the biggest problem in the energy industry? The biggest problem is that energy is a commodity. There is nobody who can differentiate between electrons coming from fossil fuel or electrons coming from a windmill. Nobody can do that. They are the same electrons. You are competing in the market of electrons. And if you are competing in a commodity market where the customer cannot differentiate, it is not a perfume made by somebody special that you think, oh, wonderful name and a brand and so on and so forth. This is not a branded product where you can differentiate. This is not a Rolls Royce. This is the same commodity which is coming out of everybody who is producing it. So a customer cannot differentiate the product that he is consuming at the end. And the interesting thing, he doesn't even consume it in a way that you think. What he does is he gets a service out of it, something entirely different. Heating, cooling, lighting, or whatever it is. Energy itself is uninteresting to customers. But even if it is interesting as energy, you cannot differentiate. Now, if you cannot differentiate a product, the only way you'll buy it if it's cheaper. That is the definition of a commodity market. You are competing in a commodity market. And you will be entering a commodity market, just producing the commodity in a slightly different way. So have it in mind. That is conclusion one. That we can agree upon. The second is, apart from the UAE or GCC region, where the governments control and their vertical monopolies in the utility industry, most of the industry is in private hands. This system is controlled by private people. And what drives them? Profit. They want to make money. That's why they provide this thing. Okay? Now you will say, oh, there are federal and local governments and they have regulations and they have a regulatory influence and they can do this and that. Would you believe me if I told you that the regulatory people have no interest in changing the supply system? Or you'd say, no, Kalle, that is not true. It is absolutely true what I am telling you. They have only two interests: system stability, that nothing happens with the system. The second is no cost increase. So anything that you bring in which is new, which they are not familiar with, they think it's going to disrupt their system. So it is the security of supply which is critical for their performance. If you are a regulator, you are looking for the security of supply to the customers. As a regulator, you don't want any disruption to come into the system. The second is you don't want to make it expensive for the customer. So regulatory people are the most conservative people that you will come across. They have absolutely no interest in changing the system. So please bear it in mind. If you want to bring about a change, you don't run to the regulator. The second thing is, apart from this region where there's tons of money, probably not anymore, but most of this investment in the sector in rest of the world is done by the private sector, not by the governments. In the United States, the private sector invests about 25 to 30 billion US dollars each year in the utility sector. Most of the governments do not have this kind of money around the world. So the governments cannot invest themselves, they are dependent on the private sector to do it. And now that brings us to the third conclusion, which will be nice for you to know. What the industry, if it is going to get into energy, it's going to make a 30 years investment. Whatever it is going to stand there for 30 years. Easy. So they calculate a return on a 30 years basis. Not on a 2 years basis or 3 years basis, on a 30 years basis. And they want it to be legal and predictable. They don't want the legal system to change so that their profit is disturbed for the next 30 years. Otherwise they won't invest. And the government is not investing, it's the private sector which is investing. And that is the condition one for them to invest. Now, if the energy supply innovation at scale is going to take place, there are only two things. One is profitable. It has to be profitable. It's a commodity market, or it is mandated, forcing one way or the other to act. So now it comes to the energy transformation which governments enable. Look at the word enable. Enable is to support to a change. Okay, what is this business about? Many people say, oh, they are risk avoiders. No, they are big risk takers, but they want it to be a managed risk, predictable risk, and with a very long time scale and very large capital scale. Remember that. It's a long time, 30 years, and lots of money. If you are going to put up a nuclear reactor, like here they are putting up, it's 8 billion US dollars that baby costs. The nuclear reactor here which is being constructed is 8 billion US dollars. And that is what it costs everywhere. Now if you're going to put $8 billion for a 30 years period, you want your risk to be managed. So it's a huge amount of money which is required, and it is required for a very long time. Got the industry right? Have you understood the Okay, what can the governments do? The government sets the playing field, under what conditions the energy is going to be supplied. They can support research, pre-competitive research in different technologies. They can support technology transfer, and they can support demonstrations, and they can create knowledge and facilitate knowledge. Now let's get to the drivers of change. Let me take you through historically a little bit. There was something which was called the Seven Sisters. Have all of you heard of them? Okay. There were 7 oil companies there was one which was owned by the Dutch, British Petroleum, rest were American companies. They were called Seven Sisters. They were used by the British and the Americans as their foreign policy tools, because they controlled governments. They were extremely powerful, and they controlled customers. The countries which were using oil was distributed through these companies, and they could really squeeze any country by stopping supplies or reducing supplies or doing anything that they really wanted to have. So they had an enormous influence over the governments, and they were an extension of the British government's foreign influence. They were an extension of the American government's foreign policy. In that sense, it was of interest for them to get into oil, to control oil, and to control all oil activities. It made sense to them to do it as a foreign policy activities. And the funny thing is that the attack on Pearl Harbor by the Japanese, the reason was that I don't know if you would you be interested in that history, why it happened? It was like this. Germans attacked France in 1940. Kaput, France was gone. Now the question was, if the mother country has ceased as an independent country and is occupied by another country, what is the status of the colonies? Now, if you are a French colony, what is your status, since France has been occupied by Germany, is not an independent France anymore? Anybody with a legal answer to that question? Okay, that was the situation. 1940, France has been defeated by Germany, occupied by Germany. What is the status of Vietnam? The Japanese did their own interpretation. They said the colonies were a free game, because the mother country had ceased to exist, so thereby anybody could occupy their colonies. So they moved in and occupied Vietnam in that process, because they thought France didn't exist as France anymore, so Vietnam as French colony was a free game, which of course the British were very unhappy about. So the British spoke with the Americans. So the Americans and British together squeezed all oil supply to Japan. Thank you very much. All of a sudden there was no oil coming to Japan. Now this is the situation that you are facing. So they said, oh, the Japanese immediately went to Washington and said, we are interested in negotiating with you about our withdrawal from Vietnam. The British, being British, said to the Americans, ask them to leave even China. Sorry, they said. We thought we are going to discuss Vietnam. You have added China to this list now all of a sudden. We are not asking you to leave China. Why are you asking us to leave China? We have been there for as long as we can remember. No, you will have to vacate China. To that the Japanese answered, up yours, and went to Pearl Harbor and attacked them. So it all started with these companies. So that is one example how they were used as an extension of the foreign policy. So they were really very powerful, and they were extremely powerful in this region, especially in Saudi Arabia. And they were extracting, at that time in 1930 to 1940, at 10 cents a barrel. That is what Saudi Arabia got. So now you can imagine from 10 cents to $100 a barrel, there's a slight difference. But that is what they were getting when these people were in power, because that way they could fuel the development of the Western economies, especially the United States. Anyway, they controlled the global petroleum industry from the 1940 to the 1973. They controlled 85% of the world petroleum reserves. They are not doing it anymore. With the result, they are no longer a foreign policy imperative for the British or the Americans. So that interest is gone. That interest was there as long as they could be used to do something interesting. Now it has become a liability for the Americans and the British. They have no interest in this thing. So that is one fundamental change that has taken place since 1973. So have it in mind. The rules of game have changed. Now the others control the oil. Okay, now the situation is, if you look at the GDP growth in the Western countries, it's very small. 1% here, 2% there, 3% there at the most, and so on and so forth. And it's countries like China which are growing, but not the Western world. I mean, here you can see this is Portugal, negative growth, Italy, negative growth, Hungary, negative growth, Spain, Czech, Netherlands. I mean, you can go around. So that is one of the problems. Have it in mind that the economies in the Western world are not growing as they were growing before. The second is unemployment is increasing in the Western world. If you look at the European Union, this is the way it is going. Higher unemployment and stagnating economic growth. This is the situation now you are facing. And very high energy dependence. If you look at, this is European 27 member countries, if you look at petroleum products, it is 85% dependence that they have. So it is a question of security, which has also come, that we are too dependent on foreign supplies. Okay, three factors. Very small or slow economic growth, higher unemployment rates, and a sense of insecurity that we are dependent on foreign supplies. Especially the Americans. The Americans pay $1 billion a day to import oil. $1 billion a day is the cost of importing oil, which is about 45% of their required 55% they produce themselves. So 45% they import, and they pay $1 billion a day. With the result, every president for the last 20 years has been talking about reducing oil imports. If we start with Carter, that was 1977, we are talking about Carter. He said, beginning this moment, this nation will never use more foreign oil than we did in 1997. Never. That was what Carter said. At that time, they were importing 40.5%. And that was in 1979, sorry, what Carter said. Okay. Let's go to 1981. That is Ronald Reagan. By then, it has increased from 40.5% to 43.6%. That is what never of Carter had ended into. So that it has increased by 3% when the president had said never, we are never going to import. So now they are up to that. And then Reagan said, while conservation is worthy in itself, the best answer is to try to make us independent of outside sources to the greatest extent possible for our energy. Reagan, 1981. 1992, it had increased to 47.2%, and then George W. Bush, the elder, he said, when our administration developed our national energy strategy, three principles guided our policy, reducing our dependence on foreign oil. 1992, now we are up to 47.2%. And then the younger George W. Bush said in 2006, Breakthroughs will help us reach another great goal to replace more than 75% of our oil imports from the Middle East by 2025. The point I'm trying to make is that oil imports have become an issue. Because it is enough money that is going out of the country and your economy is not growing. So you don't have that much reserves to play on. So there is an interest to do. So there are two things. One is oil companies are no longer an extension of your foreign policy as United States or Britain, so that you think it's an interesting thing to play with. You don't have that leverage. Now you have to pay and you have no influence. So with the result, they think that this is tons of money which is leaving the country in an economy which is not growing. That is the basis of not that they have woken up and said, oh, there are so much environmental problems, the temperatures are increasing, so let us do something for the betterment of mankind. Oh no. Oh no. It is just that they are in an economic difficult situation, and in order to get it, they have to save. And they think the saving which does not hurt the country or the voters is to reduce oil imports. And that process is taking place. And that is the driving force which you have to remember. With me? Okay. That is the basis of new industrial revolution. It's not based on altruistic things. It is based on pure money, interest. And you have to remember that nations always pursue, Western nations at least, always pursue their interests. Okay? All right. Now, what are the bases which are going to bring about this industrial revolution? The first is the policy. The policy is let's do something about it. Let's get into alternatives which will make it possible for us to keep as much money as possible in the country rather than sending it out. The second is, in order to achieve that, you have to have the technology, which is in a commodity market can maintain itself. Don't forget it. It is a commodity market. So you have to develop technology which competes with established technologies on cost basis. And the third is the market conditions, which I have explained to you. Okay. The first thing which has happened slowly, but has come to fore now, is digitization. What the devil is digitization? It is the use of computers to simulate things. And it all started in 1990. In 1990, the superpowers who had nuclear weapons, Russia, United States, France, England, for example, got together and they decided that they would no longer carry out underground nuclear testing, which was very common practice. Okay, now you have tons of nuclear weapons and you have to know, if we press the button, are they going to do what they are supposed to do or not? How do you know it? In order to be able to get an answer about the availability and reliability of the weapons, mass destruction weapons we are talking about, beautiful things. So they had to have some sort of simulation method to figure out that this thing is really going to get to the target and going to work. That required high performance computer modeling. That was the only way that they could do. It's not very different from a simulator in an aircraft. They train you basically in a simulator and then you sit down in the real aircraft and it performs the same way. That is how they make pilots. Because flying an aircraft is very expensive. So you just can't have two people flying an empty aircraft just because one is training. is you put them in the simulator, and that is a lot cheaper, and the simulator trains you to do it. In the same way, you had simulators to test nuclear weapons, that they would function, and they functioned. Okay. With the result, from 1990 to 2005, the performance of the computing capability had increased by a factor of 10,000, which is a lot. And with that result, you could integrate experiments, and you could have predictive capabilities in your computers, which was not the case before. Now, when we are talking of high performance computers, the expression that is used by the technical people is petaflops. Are most of you familiar with petaflops? Petaflop tells in billions that you can do the calculations in a second. I mean, if it is 3 petaflops, you are talking of something like 6 billion equations per second that it can solve. So it's that type of animals we are talking about, really big babies. Now they have crossed 12 petaflops, and they are moving towards 20 petaflops. So they are really becoming extremely powerful. Now the interesting thing was that these computers were owned by the government, and they were not available to the private people. But in the year 2000, the government of the United States and other governments made it available to the universities and research faculties. Now they could use those computers to do their calculations and simulations. All of a sudden the world changed. And this has been brought to the world of energy to a large extent, and predictive simulations make it possible to shorten the period between research and deployment. Otherwise, it was very, very complicated to prove different parts that they will function and it is worth investing in them and so on and so forth. Now you can have that predictability through simulations for the investors to see that this thing would work, which was not possible before. So that is the role the digitization is playing in shortening the period between the concept idea to deployment. Boy, what happened here? Yes, here we were. Okay. Anyway, I have taken 2 products. One is the Cummins engine on the left-hand side, which was simulated, and then the tires. But the third thing, which is actually interesting, is that there is a company in the United States with the name Pelion. They wanted to develop a new battery, and they wanted to know what type of cathode material they should use to combine, which will best combine with their magnesium anode. They had to figure out. Now, they couldn't test one material after the other and the other and other. That wouldn't have been possible. But anyway, that was what Edison did when he developed the first lamp, is that he had to test everything himself to see what would hold together the lamp and would burn. And in this case, they had to do it. What they did was that they did a computer simulation of different materials, and they ran through 10,000 potential cathode materials in no time to figure out which was the best material to use with the anode in the development of a new battery. That immediately shortened the whole process, reduced the costs, and gave them an optimal result. That is how you are using computer simulation now to a large extent. In the same way, when it comes to fusion reactors, for example, you can't just build something and test it and then not test it and so on and so forth. It was tested through digitization, and now they're constructing 2 fusion reactors in the United States. So that made it possible. So even in your life, you would see that simulation will play a very, very important role to see how things are going to interact, integrate, and perform. And you will be able to verify, and you will be able to test. Okay? Are you with me? Digitization, you have got it? The second thing, where nothing had happened for a very, very long time, and which is happening now, and without this, you would not get any smart grids that everybody is talking about. What really is the critical issue with smart grids? I mean, there are lots of things about security and so on and so forth. But as far as the technical performance is concerned, it hangs on power electronics. And one of the biggest components in power electronics is the transformers. You have small and you have big transformer. Now this is a big baby, which weighs about 3,600 kilograms. It's an American transformer, that's why it's 60 hertz. If it would have been European, it would have been 50 hertz. And then it is a distribution transformer. And if you look at today's power grids, the biggest problem is that they are, the power flow is only in one direction, from the power company to the consumer, and the transformer transfers electrical energy from one circuit to another and transform it to a more usable voltage up or down. That is what it does. It doesn't do anything fancy. And this is how it looks. It's a huge thing. This is what has happened now. This is already there, but it hasn't come out. This is solid state transformers. A solid state transformer actually has only been possible because you developed the basic building block of a solid state electronics is semiconductor components. That is the basis around which you start. And in this case you need, for example, field effect transistors, FETs as they are called. That's the building block around which you build things. And there has been an enormous capability through gallium nitride and silicon, especially silicon carbide. They have come with semiconductor components in silicon carbide, and that has brought about a huge change. Now if you were to look at a silicon carbide, you can make a 200 micron silicon carbide which can handle 15 kilowatt at 100 amps. That doesn't say very much, but let's put it this way in a very simple term. It can handle 1.5 megawatts of electricity. That is a big baby. And now if you operate it at 100 kilohertz, the first thing that I showed to you weighed 3,600 kilograms. This thing weighs 45 kilograms. Voila. You can put it in a little suitcase and carry it with you. That is all of your transformer. This is one of the key breakthroughs. If I were to be asked what is one of the 10 biggest breakthroughs for the deployment of renewable energy and others, this is one of the key things that has happened, is the development of silicon carbide MOSFETs. And it has an extremely less footprint. The cost to install a transformer could be 10 times the value of a transformer, but this is very small. But that is not the only thing that it does. It does many, many funny things. The first one had flow only in one direction. This has flows in both directions at the same time. And apart from step up and down voltage, which a normal transformer also does, this also does. What it does is, it can change the power characteristics, which is voltage and frequency. Why is it of interest to change voltage and frequency? If you are charging an electric vehicle, you can charge it much faster if you can change both the voltage and the frequency, depending on the car that you have in front of you. You need a very flexible charging system that offers you that. It can charge it very, very quickly. The other is, it improves the power quality. I mean, it can take care of harmonics, third, fifth, ninth, and so on and so forth. And the other is that it has the communication capabilities, which an ordinary transformer doesn't have. You have telemetry and so on and so forth. And then you can have integrated storage in it. The interesting thing is that all of a sudden, this thing makes it possible for the flow of electricity to be controlled exactly the way as data is being controlled in internet. It will be flowing the same way. Now it is, as I said earlier, This I have taken. What is happening here is that you are increasing the current density 4 to 8 times. That is what makes it that you can need a very little equipment, because the current density is about 8 times higher. And power density is about 4 times higher, and switching speeds are extreme. So this is what you are offering. This I have gone through, silicon carbide. Now let us see, where is power electronics used apart from in the net? All this is power electronics based. All these use similar components. So this will not be limited to just producing a big transformer out in the middle of nowhere. It will affect everything that you are using in your home and in your daily life. It will change everything. So the power electronics is the key to market transformation, and that is what they have cracked. So that is one of the bases, because it will affect all these products. They will all move towards solid state now. And they haven't been able to move before towards solid state because you didn't have the basic components and building blocks to do it. Now they have. Are you with me? The breadth of this technological breakthrough is huge. Because now refrigeration, for example, instead of having compressors and so on and so forth, would move towards solid-state electronics for cooling purposes. With the result, whole of the system, instead of looking this big, will look this little. And will consume something like 10 times less power. So that is how you reduce energy intensity, and then it will last forever. You can pull it out of an old refrigerator in your tire and put it into the new one, and it will still work. So that type of thing is happening. Okay, when it comes to PV, the issue is not only the performance of the cell. That is moving towards 28% efficacy, system efficacy. They are moving towards flexible systems which are bendable, foldable, and so on and so forth. So that part is taking place, and they are moving towards cost, which total installed cost. Since they are flexible, they are lighter, they are easier to install, so you don't need huge frames as you have had over, and then supporting structures to keep them in place, and all that disappears. So in that sense, the cost would come down below $1 a watt by 2020. What is the problem that they are facing is what do you do when the sun is not shining? That is actually the technological issue that you have to take care. I mean, when the sun is shining, everything is wonderful, hunky-dory. But the question is, develop technologies which make it possible to use your PV system when the sun is not shining. That is where the emphasis has shifted now. And that is what I would like you to know. That is where real work is being done now. And there are two things. One is hybrid solar energy converters, where you are producing both electricity and heat. And in a more efficient, the third is that you are developing a system which uses the whole solar spectrum. Not just a portion of the spectrum, but a whole spectrum. But the most important is hybrid energy storage system. In a cheap, efficient, and a big way, you need to store energy so that it is available to you when the sun doesn't shine. And you shouldn't have a battery which requires whole of Sahara Desert, as a matter of fact, to be able to support you. Okay, so what is happening? Stationary power storage is the critical issue that they are working on. And what is the problem with the current storage systems? if you were to ask that? The current storage system is that they have very low energy density. That is the biggest problem. Since they have low energy density, you need huge batteries. Very simple. Are you with me? Makes sense. So if there is low energy density, you need a bigger battery. And which automatically leads to much more space. And then you have to pump the fluid very rapidly, which in turn reduces efficiency, because you can't do it without using energy. Now you have to pump it, and while you are pumping it, you are using more energy, and you are inefficient from the beginning, you become inefficient. Voila. But new batteries are coming. One of the most interesting is from your sister organization, MIT. They have developed this battery, which has become a private company, which is called 24M. And they have produced the best lithium-ion batteries, and they have fluidized the electrodes. They are no longer metallic as you know them. And they have a gluey substance which is not floating like an electrolyte. And they have attained a 10 times improvement in energy density and have much lower manufacturing cost. And they are talking about $60 per kilowatt hour. They are moving in that direction. The cheapest actually today is to store water in hydro. The big lakes that they make behind hydropower stations. That is the cheapest storage that we have today. And do you know how much does that cost? It costs $100 per kilowatt hour. That storage. So they are heading to $60 per kilowatt hour. This makes PV and wind all of a sudden interesting, because wind has a tendency to blow in the middle of the night, where people are sleeping, most of them. So your energy requirement doesn't peak out, and your energy production peaks up. Or it is seasonal. It blows at a certain time of the year, and that's rest of the time. So you need to store it somehow in order to be able to use it later on. With me? And this is how this bluey thing looks like. The electrolyte in the battery, 24M, and this is $60 per kilowatt hour. Ambri is another company which is working with low-cost salt electrolyte and which is very cheap, molten salt electrolyte. And they are producing in 500 kilowatt and 2 megawatt storage capacity, and the finances of them are Bill Gates, Renault, Tesla, and Total, which is a pledge oil company, which is supporting this battery. Total is an oil distributor, a huge current oil distributor. And then I couldn't resist to take this mobile battery. This is how it looks. And it is actually battery created by screen printing. And the idea is to make it a part of clothing, military uniforms and so on and so forth. So they can really run lots of things which are a part of their police and so and mobile phones or whatever they have, so this will support other activities too. And this could also have sensor integrated things. For example, I mean, you don't ski very much in this part of the world, but when you have Levine, when lots of snow comes on you and it's very hard to find you. So if they have a sensor which was sending a signal where you are, which could be made a part of the ski dress, then you could have a battery like this which will immediately start sending a signal to somewhere up. And you could also have this aircraft recorders and so on and so forth. They are much bigger batteries now, which is a problem when you drop them into the sea. So this will really work. But the most important is to make it a part of the military clothing and military uniform. So this is taking place. We are moving towards storage around $60 per kilowatt hour in stationary applications. Okay, we have improved power electronics. We are improving storage. These are disruptive technologies that they will make it possible for a change. Let's look at transportation now. Transportation has not been a part of the electricity system so far. It has its own life, living on the side. This is how transportation looked in 1880 and 1890, and this is an omnibus. And you would put women on the inside and the man on top. That was the principle, because they thought that these fat men had it easier to climb the ladders, which of course is the other way around. Women had it easier to climb those ladders than these very fat men. But that was the thinking which they were at that time. The fat men had to climb the ladder, and not so fat women could sit. And this is how it looks. This is a real scene, and you can see all these are horse carriages. It took 30 years just to transform this world from horse carriages to something else. Just 30 years between 1880 and onwards. And why was it transformed that very quickly, extremely quickly? Is this. They had the world's first urban planning conference in 1898 in New York, and whole of the world got together, and the agenda had only one item. That was not how to plan beautiful cities with bicycle ways and the bus ways and so on and so forth. It was how to get rid of the horse manure in the cities. Wonderful title. And it attracted many, many cities and many, many people who came around. And what was the problem with horse manure? I mean, it doesn't look that big a problem. There were 160,000 houses in Brooklyn and New York, which are just those very small areas in New York City, and they were producing 2 million kilograms of horse thing a day. Now, as long as there was a market for it, which was initially there was a point to collect it, because now you could sell it and you could make some money. It was a commodity market where manure was a commodity which was available to the farmers. All of a sudden, when you were producing it in enormous quantities, then the market, the bottom fell out of the market, as the expression goes. There was no market. If there was no market, the horse owners had no interest in having it picked up. They let it lie there wherever it was lying. So with the result, you had about 2 million kilograms of horse manure which was adding to your street every day. Welcome to the club. Now, if you want to walk on that road, there were people standing in the corners. They will charge you a little bit of money to pay a little bit of path around which you could walk through it. So if you didn't have that money, good luck. And there were other products which were joining it, something like 40,000 gallons per day of urine, and flies, 3 billion a day which were being produced, and the other issues were so on and so forth. Then the railroad was introduced. Now that added to the problem. Rail was fine, but rail moved between one fixed point to the another. To load the rail, you had to have the horses, and to take away the products from the railroad, you needed horse carriages. So that increased the number of horse carriages to feed the cities. All right, let's forget about it for a while. So it took only 30 years to get rid of it. Everybody was saying, this is not a manageable situation, let's get into something else. So they got into other fuel-based things. Let's look at transportation today. The options that we have internal combustion engine-based transportation. We have hybrids, and we have what else do we have? Plug-in hybrids, and we have battery electric vehicles. That is what we have. Okay, is the internal combustion engine dead? The answer is no. They have also woken up after about 100 years and have started working on internal combustion engine again. When it came to a traditional internal combustion engine, it has 4 processes, or strokes as they are called. I mean, it has an intake where the air comes in, and then fuel comes in, and then it compresses, and then it moves the camshaft, and then exhaust. That's it. So it has 4 strokes. Now they are developing engines which have only 2 strokes, intake and exhaust, nothing else. With the result, you need 3 cylinders and not 8 cylinders or 10 cylinders as you have in lots of vehicles here. You need only 3 cylinders. You just make the figures. And there are pistons which are feeding the same hole, 2 of them. So what has happened now is that there are no cylinder heads in the new power design, and there's no valve train, there's no camshafts, there are no push rods, there are no rocker arms, there are no valves, and there are no valve springs. All that is finito. Their absence lowers the friction, reduces engine size and weight, and minimizes cost. What is the efficiency of these engines as compared to the current ones? About 50% more efficient. So you'll see them up and running, and this is what it looks like. So internal combustion engine is not finito, is not dead, is not gone. It's going to become much better. But it is just because the competition from alternatives is coming, so these people have woken up and have started doing something about it. And that is always, you must remember something, as you grow up, which I must tell you. Industry is not moved by the opportunity. You won't believe a sane industrialist or anybody is moved by there is a great opportunity. Let us explore. No. The prime mover of industry is threat. You have to scare the hell out of them, and they immediately wake up and start doing things. That is how they work. Because they get entrenched, they're quite comfortable with their position, the customer base is stable, things are working out like that. But if you threat through a disruptive solution, they wake up immediately and their eyes pop out and they start doing things that they should have done a long time earlier. So have it in mind, as a matter of fact, that if you start working for companies, which most of you will do, and you think I have this very brilliant idea about an opportunity I could get my managing director and I'm talking and he says, you are a genius, my son. I am so happy to meet you. Wonderful, wonderful. I wish most of my employees were like you. No. You go and tell him how his company is threatened and his personal position is threatened. Have to be this motive. Okay? That was just something to carry on the way. Okay, the transportation as it is about oil and gas. Oil, not gas. Oil and diesel is about 25% efficacy in the engine. And the reason is that you start with 100% here and just pushing the pistons down to get more air and fuel into it takes 35% of your energy. Just do like this, 35% of your energy is gone. And then the rest is consuming. So what is left after having done everything is about 25% is converted into driving the whole thing forward. So it's not really very efficient way of doing things. But that is how we have been doing for a very long time. And let me sort out this thing because now I have got it thoroughly entangled. So bear with me for a second so that I know in which direction I am going. Okay. That was it. Now okay, if we get into natural gas, and if you were to look at it, these are the American studies in long-haul trucks. To convert the system to be able to work on natural gas cost about $100,000 in a truck, and it has a fuel saving towards diesel is about $40,000 per year. And for a fueling station to do it, it costs about $1.6 million to have the system to put in the gas into it, and the payback period is about 2 to 3 years. This is also payback period 2 to 3 years, and that is taking place even in UAE. They have forced the taxis to put in gas cylinders into them. So in that sense, people are moving towards gas, so it is not really. But this is an in-between situation. So first, the internal combustion engine is improving. Meanwhile, people are moving towards gas to save diesel. So that is taking place. Okay, if we look at an average Western car and convert it into electric energy, whatever they're using, they use about 80 kilowatt hour per 100% kilometers. Per 100 kilo, and I'm counting as most cars I see is 1%. That is how most cars are driven. 1% is sitting and is driving the car. In this situation, the car is not using any energy, but if it is running around, it will be using about 80 kilowatt hours per 100% kilometer. This is an oil and diesel-based car. Wonderful. Now let us look at it. What are the four fundamental principles? The first is to make them aerodynamical. Why? Because then you have lower air resistance. And if you have extremely low air resistance, you can save up to 20% of your energy. Just by designing, that is why they concentrate so much on aerodynamics. Because the energy saving is huge. So really well done aerodynamics can save you up to 20%. And that reduces the air resistance in front of you. The second is to lower the weight of the vehicle. And why do you want to lower the weight of the vehicle? Because it's easier to roll. That's what you wanted. You want it to roll. And the other is you have less brake losses. And the third is to convert energy efficiently. That is what you want it to do. And the fourth is to use energy efficiently. That has to do with speeds and the way you drive. If you do too much, then you consume more energy. If you drive too fast, you consume more energy. So in general, you could say they have done studies in the United States and said everybody followed the speed limits. Energy efficiency of the fleet was increased by 12%. In Europe, they did studies and said, oh, forget about everything. If you just check the tires of your cars and kept the pressure right, you would save about 5% energy. You don't have to do anything. But that doesn't increase the total efficiency. It is just that you get rid of the inefficiencies that you have created by speeding up too much and so on and so forth. That is an inefficiency on top of that, and that you can bring down. Okay, how do you think the vehicle looks like which meets all these four requirements? How do you think it's going to look like? Want to see it? This is how it looks like. This meets all the four conditions. And it consumes 1 kilowatt hour per 100%, and it can take 3 people. And it can be run on any fuel. It has a little motor attached to it, and it can run on any fuel. And if you are willing to ride anything like this, you will be meeting all the physics principles of a very efficient electrical vehicle or biofuel-driven vehicle or whatever it is. And if you put a little carpet inside the street, you could sit on the carpet very comfortably and easily if you want to. If you are willing to ride in a thing like this. Of course, you don't. That's the trouble. How about riding in this one? There's also an electric train. Now we are moving from 1 to 6 kilowatt hours per 100% kilometer average, or 3 kilowatt hours per 100% kilometer average before. And then you say, no, I don't want to sit with all these strange people, and then I catch cold, and they'll be spitting there, and they'll be doing strange things, and they will be putting fingers in their nose, and so on. I don't want to see all that. This is not my style to go around with 6 other people, strangers, and so on, so forth. Not very nice. That's why we don't get into a thing like this. Then you have plug-in hybrids, as it was. Now you are up to 25 kilowatt hours per 100 kilometers. You have this option. Or if you are not very tall and very big, you can have this kind. And it is 1.3 kilowatt hour per 100% kilometer, but you have to be a teenager to get into it. This will give you 3,520 kilometer per gallon at 24 kilometer per hour, if that speed is acceptable to you. The average speed in major cities in the world is about 15 kilometers per hour. People in Rome, they are driving 100. High Ferrari can go do 300 kilometers. They still be driving 15 kilometers an hour in the evening. Doesn't matter whether it's a Ferrari or it's a bicycle. It's 15 kilometers an hour that the traffic allows. There's so many cars in Ferrari. You can't fly in a Ferrari unless you do that. That must be what you have to get. So this is actually a very acceptable speed. When the tank works and come back next year, that is just about that you'll be driving it over here. Put another gallon in just 2 for 3 years, 3-4 gallons it will take. So there are interesting options around, which not many people are interested in following, but they're there. So we have come in this. Most people think that we haven't done anything or nothing has happened. What has happened? People like fancy cars here. How about this kind of stuff? Looking like this, or looking like this, or looking like this. You are still using 6 kilowatt hours for 100 kilometers. Or Tesla, 15 kilowatt hours per 100 kilometers. This hasn't been used in this part of the world, but this is excellent stuff, electric scooters. And they are 3 kilowatt hours per 100 kilometers. This you have to remember as an academic exercise, which is extremely important. The trouble is that if you were to make vehicles extremely efficient, do you know what will happen? People will start getting rid of it. So you have no control. But now you'll be consuming more energy than what you were consuming because this is what we have observed in many areas. You make lighting more efficient. Light emitting diodes, they are extremely energy efficient in relation to consumption. All of a sudden you see they are putting them under the bridges, they are putting them in fountains, they are putting them in water there, and they are putting them everywhere. Where there was no lighting before, you start seeing light emitting diodes. When you walk even in this city in the middle of the night, then you will see this very tall, a long line of LED and blue light which is good. It wasn't there before because you couldn't integrate into the building architecture because the size of lighting was too big. All of a sudden it's a small piece, very easy to integrate. So the lighting has become efficient, but the amount of lighting that you're using has also gone up terribly. So the question is, are you saving anything or not? Each one is very efficient, but cumulatively they're consuming more than what we were consuming before by using them in places where you didn't use it. You make cars more energy efficient, my feeling is that people will start getting cars bigger than the buses. They can just sleep and lie down and do everything. A sort of little living room that they carry with them, with the children sitting there and doing everything that they do at home. And that is called Jevon's paradox. Is that we make things more efficient when people start using more of them. Okay, let's look at the battery, because that is the key component in electric vehicles. This is a taxi from 1900. This is how a real taxi looked like. And all this, by the way, is battery. That is the battery. And this is where it carries the batteries. And this is where it carries the battery. So you can see the division of vehicles between the load-bearing part, which is the drive it, and the passenger load-bearing part. Okay, let's see what happened. I mean, this is an electric vehicle, whether that will give the drive. If we go back to the past, and we look in the year late 1800, the electric powered cars were the highest performing and most popular vehicles. And why were they popular? They were not smelling anything, which the gasoline vehicles were. They were quieter. But there were two most interesting things with them. One is, the cars at that time didn't have a starter. It was a key, go like this with a key, you couldn't. You had to go out and use a crank. Have all of you seen a crank? You understand? I mean, those of you who are in my younger than me, you have, but all of you, are you familiar what a crank is? Or is there anybody who doesn't know what a crank is? There was a little hole in front of below the radiator. And then you had this metal thing which looked like this, that you put into it, and then you had to crank it. That was called cranking. And that started rotating the engine. But you had to physically yourself rotate the engine, whereby the piston started moving. Now you have this electrical ignition on, but you have to move the pistons first before you got the spark into them and they start rotating. So you have to do it. And you couldn't do it if you were a woman, because it was a very heavy thing. It was not very easy to do this cranking. And the other thing was that changing the gear was an exercise which was not of this world. You had to press your clutch 3 times before you could get to the gear. The first time you pressed it and you moved it from one position to the other position, the second time you had in the and then you would yes. And so it was. Now you didn't have to shift gears in an electric vehicle. You didn't have to do cranking, which people thought was a little bit unbecoming of gentlemen to stand there on the road and to do this type of cranking if you are wearing a big tall hat. I mean, you're dressed all very nicely with this big hat with white gloves, and you're standing there with the flowers, with things, you look sort of safe and very unbecoming of a gentleman. And the ladies would never do it. So that was all solved. So that is why they were extremely popular. Okay? But what happened? What went on? Oh. Okay. What were the main? The main customers were the taxi fleets. Now the taxi fleets the battery lasted only a certain number of hours. There was one company which was supplying the cars and the battery. They would change the battery after every shift, so each morning they were. All of a sudden, the market exploded for the taxis. But the battery side didn't catch up with that. So they couldn't supply the batteries as rapidly as they were required, because that capacity could not be built. So now the taxis were not getting the batteries as they needed, and the company could not supply them. So they went bankrupt in 1907. And now it has taken more than 100 years to get back. And would you believe that the problem is the same? The range of the battery is very limited. And how do you change the battery to get a bigger range? You don't have the infrastructure to support it. So the problem is identical, the situation is identical, it's just that 100 years have gone in between. The issue even today is, how do you very quickly recharge a battery? How do you get a range in the battery? Same problem that you had 110 years ago. So batteries are the key to solving this problem. Okay? Let's look at the batteries. These are, do you want to have a break or something, or shall I go on until you are lying here and are totally dead? Whichever is acceptable to you of the two propositions. Would you like to have a short break? The whole of it? Yeah. I mean, it will take about another half an hour for me to finish this. What's the difference? The day is anyways point. Have a 5 minutes, 10 minutes break. Okay. Is it okay? Or would you want me to continue? Whichever way is Convenient.
Just continue to continue.
Okay, fine. All right. We are on that many, so I'll try to run very quickly. We are 56 and there are 73 slides. Okay, this is basically lithium-ion batteries that we are using, and they're the same batteries that you're using in cell phones and laptops. And the electric vehicle batteries require thermal and mechanical safeguards to prevent overcharging, overheating, and cell damage, because they have to last for a certain time. And the range is only 160 kilometers in best batteries that you can get on a single charge. And it takes very long to charge them. And the batteries cost about half the cost of the vehicle that we have inside. What we need is batteries which will compete with gasoline. For that, we have to increase the storage capacity by a factor of 2 and bring down at 30% of their current cost. Otherwise, they won't be able to compete. And we will forget about this one. What we are looking at is to have an electric vehicle battery that will travel from Mustafa to Ibri. I don't know where Ibri is, but I looked at the internet and found out that it was a city somewhere 480 kilometers. So I was just looking for a city because 480 kilometers and it's a Ibri. Huh? It's in Oman? Wonderful, thank you very much. So anyway, if this should be able to, what they believe that they can do in a very near future is to produce a battery which will be able to cover 480 kilometers at $10, which is 36.5 dirhams. And I made a calculation at gasoline prices as we have today, it is still slightly more expensive. So we are not really there, but pretty close. At 1.7 dirhams a liter, you are still slightly cheaper. And there are batteries coming. I'll tell you the companies which have come a long way in this area. This is NVI, one company which is making the 480 kilometer range battery, and the whole vehicle will cost 25,000 to 30,000. And the companies which are backing this thing up are the General Motors, Ashai Kasai, and then there are lots of others. So this is the battery which I believe is closest to coming out on the market, which the automotive manufacturers believe and trust. So I thought you should know which company is coming. And this is another company which is coming up. This is also a lithium-ion battery, and they are using non-structured silicon material and so on and so forth. And they have raised fairly good amount of capital to do it. All right. So these are the two companies which I believe it is. Now the second thing that I discussed out of the fourth principle was reducing the weight of the vehicle to lower the rolling resistance. For that you need lightweight metals, you need carbon fiber reinforced polymers and multi-materials. Now the question is that how do you maintain structural integrity of the vehicle? I mean, it should work. And the other is it should have a crashworthiness, that you have to remember that it should be able to take accidents. So it's not just reducing weight, it should also survive accidents. So there are big programs going on to produce high-strength steels, aluminium, magnesium alloys, and composites. That is going on all over Europe, that is going on all over the United States. And they have come a long way in creating this type of thing. But I tell you something which is most interesting, then this is carbon fiber-based materials, carbon composites, which are also coming up, but they are expensive at this stage. There is an interesting thing that they're really working on, which I thought I must tell you, which makes lots of sense. What they are trying to do is to develop a solid lithium-ion battery with no protective packaging at all. I mean, you need a huge amount of protective packaging around a battery for the whatever fluid material it has. That will reduce the cost substantially. The trick is what they're trying to do is to make battery an integral part of the vehicle, which means that you put the battery into the chassis. Do you follow it? The load-bearing part of the vehicle, instead of it being separate, it has holes in it. So they are trying to put the battery into all those structural holes and to create those load-bearing structure with the help of the battery. So the battery and the load-bearing structure would become one and the same thing. Now you have a load-bearing structure, and inside it you put lots of battery, which takes an enormous amount of space and has its own packaging and everything, which adds to the weight to a very, very large extent. Now if you made the vehicle and put the battery everywhere, instead of just making it in a clump like this, now it will be put in wherever you get a little hole, you will put a little bit of battery into it, and so on and so forth. And you will create the structural part, and the battery would be one and the same thing. And that way you will be able to reduce an enormous amount of weight and waste that you have. What they are working on is to make it impact tolerant, to put it in a way that it can take the impact. And it will be a very widely distributed battery, which is not the case today. It is just lying as a clump somewhere, as just one piece. Now it will be überall, wherever you can possibly think, and it will become an integral part of the vehicle support structure. That, I think, is a very smart way, and there is not much which is going on in this case. And that will reduce the weight. That is another destructive thing that we are seeing which is happening. And the last is biofuels that I would like to take. Normally when we look at biofuels, we are talking of photosynthetic biofuels. And you have this kind of stuff, sugarcane, corn, apart from algae, and cellulose. The efficiency of these to convert the amount of energy which is falling and on them and what is stored and what you get on the other hand here as biofuel is about 1%. That's an integrity. That I would like you to remember that the photosynthetic processes are ridiculously inefficient. Okay? And why are they inefficient? And they normally, in the if there's anybody from chemistry or in biology, basically there's a Kelvin process that they follow. It is called Kelvin cycle. And now in the Kelvin cycle, when you get into it, that is to bond carbon with carbon, which is a carbon bonding process that you're working with. The trouble is that it uses an enormous amount of heat when it gets to. So the Kelvin process itself is very inefficient. The other is that the production of biomass that you are going to use for it it requires water, it requires fertilizers to grow crops, and it requires very large areas to grow them. And then there's a cost of collection. You can't collect it over 200-300 kilometers area. You can collect it only 50, 60, 70 kilometer area. And the problem of transportation and storage, because it's a low density product that you're talking about, so the volume weight relationship is against transportation. It's a huge volume with very little weight that you have to transport, and it's basically a dry substance that you're going to convert it into biofuel. So it's ridiculously large amount of material that you have to transport, and it is it's difficult to handle, it's difficult to transport, and difficult to store, and it's very difficult to use in its original form. I have just a comparison here. If you were to look at coal is 700 kilograms per cubic meter. That is the density of coal. And if you were to look at wheat straw, it is 18 kilograms per cubic meter. So this is 18 and this is 700. So this is very low density material. But anyway, people have found some ways to transport it, but they're a little bit tricky. So I'll show you some efforts to bring down the transportation costs. And one of the most common is like this. This is one way to reduce your transportation costs. Do like this. Not very high transportation costs. Or you can do like this. I don't know what the Shooter, we call them. But the shooter is going to say, if the shooter was to see a thing like this coming into it, or at times it could look like this. With the side because the weight was too much. But anyway, so this is the only way that they do it, but you can't do it everywhere. And I don't think so it's legal anyway. That is at least my feeling. But I could be wrong. So this is what we are looking at. Now what is happening actually is, which is quite interesting, is that we are moving into entirely new fuel types, which are extremely interesting. These are called electrofuels. They are 10 times more efficient, and you are using hydrogen that you are getting from useless material like hydrogen sulfide, which is a byproduct of oil and gas industry and many other processes, out of which you can take hydrogen, and then you have carbon dioxide also, which is a waste material in many cases, and you combine it with electricity generated out of any source, and then you have non-photosynthetic microbes. Now you can create an entirely different cycles which are not like Kelvin cycles. And first of all, you are using most of the material which is waste material, and you are using non-photosynthetic microbes, and you get a 10 times more efficacy into them than you get otherwise. And that is increasing. They use microorganisms that do not need solar energy to grow, produce biofuels. And they use directly the energy sources. You do not have this transportation cost. The biggest issue is you do not need agricultural land to grow anything. You do not need to add fertilizers. You do not need to add water. You do not need to add transportation to it. It does all that itself. So in that sense, it becomes extremely interesting to work with this kind of material. And that is where the research is going on. And they have come a long way. And this is one of the real threats. And the institutes which are involved in this process are Columbia, Amherst, Harvard, MIT. All of them are involved into producing this type of stuff. And they believe that the electrofuels have the potential to be disruptive, which means that they can take on oil. But of course they have calculated at $100 a barrel. You can always go down to a $50 a barrel, and then you start also treating them again. But at $100 a barrel, they think they can be cheaper. And chemical feedstocks can be cheaper than from crude oil, refined crude oil. And then the interesting thing with them is, which we have to remember is since you need electrical energy to produce them, you could use them to store energy instead of batteries. Now you have stored energy in a fluid form. So they can function as batteries instead of having, so they are a potential competitor to the development of batteries, where you will be able to store surplus energy by combining the microorganisms and storing it in the form of a fluid, which you can transport to a gas station and so on and so forth, and fill into the vehicles and use it. So they become a very, very interesting energy storage thing, which you can't do with oil as it is. That is the interesting part, and that is what it differentiates from others. The other, of course, it doesn't produce carbon dioxide. So you have the advantage. So electrofuels is another disruptive technology. That's all. I'm all yours. You wanted to ask me something? Okay. Well, I hope you have understood the landscape in a bigger way. That was the idea, was not to give you technical details and not to concentrate on wind or solar and so on and so forth, which each